welcome back to chapter 3. We're talking about water and the properties of water and how the properties of water affect biological organisms. Water is a really good solvent. We've been talking a lot about hydrogen bonds, and water is able to form a lot of hydrogen bonds, both with ionic and polar substances. But before we talk about what these solutions are, let's define some terms. A solution is a liquid that is completely homogeneous mixture of substances. So if you have, like in this picture, you've just got a chunk of ice at the bottom or a chunk of salt at the bottom, that's not a solution. When that has thoroughly dissolved and it's equally dissolved through the whole substance, it's homogeneous, everything is dissolved in it, that is a solution. The solvent is a dissolving agent of a solution. Water is a great solvent. You will see it as a solvent for anything from salt water and Kool-Aid to biological substances. And a solute is the substance that is dissolved. So the salt or the sugar or the Kool-Aid or the blood serum components. An aqueous solution is any solution that has water as the solvent. Some nice little definitions for you to remember to kind of help you understand what we're talking about in this chapter. Water is a versatile solvent due to its polarity. So it can form bonds around an ion. So this negatively charged chlorine ion here is going to be attracted to the partial positives in the hydrogen ends of water molecules. The positively charged sodium ion is going to be attracted to the partial negatives on the water molecule's oxygen ends. This forms what's called a hydration shell. So you've got water surrounding a chlorine ion or a chloride ion and water surrounding a sodium ion. Any ion that is surrounded by water, that water surrounding it is its hydration shell. Water is really good at dissolving non-ionic polar molecules. So something like sugar is good at being dissolved in water. Even large polar molecules like proteins can dissolve in water if they have ionic and polar regions. So you'll still get that hydration sphere like you see in this picture. A large protein, it's still going to be surrounded by water molecules and develop a hydration sphere because it has ionic and polar regions. That means that protein will be able to flow through your blood and get to places where it needs to get in your body very easily because it is dissolved in the water of your blood. There are 3 types of mixtures. A homogeneous mixture or solution is one in which the chemicals are chemically bound. Heterogeneous or heterogeneous mixture is when the components are not chemically bound. And a colloidal suspension is when large organic compounds are dissolved in a solution. So it's going to act like it's homogeneous, but in reality, at a molecular level, it's actually heterogeneous. Some substances are hydrophilic and some substances are hydrophobic. So hydrophilic, you can kind of break that word down to water for hydro and philic meaning loving. Hydrophobic, you can break that down to hydro or water and phobic fearing. So hydrophilic solutions love water. It has an affinity for water. Something like an ionic or a polar molecule is going to be hydrophilic. It can form that it can develop a hydration sphere around it, so it's hydrophilic. It dissolves in water. Hydrophobic substances, or water-fearing, are substances that do not have an affinity for water. Something like oil or lipids that don't mix with water. If you've ever tried to mix oil into a glass of water, or if you've outside seen car oil on a puddle, oil does not float in water. Oil floats on water. It doesn't dissolve into it. Oil molecules are hydrophobic because they are pretty much nonpolar. They don't have polar or ionic regions. They don't develop a hydration sphere. They don't have any interactions really with that water molecule. Hydrophobic molecules related to oil are major ingredients of cell membranes. It's very important that your cell membranes have those hydrophobic regions surrounding your cell, which allows your cells not to dissolve in water. So, blood and water can float over your cell without your cell membrane dissolving. It holds your cell intact. That's a pretty important feature of cells that allows them to be alive. Most chemical reactions in organisms will involve solids dissolved in water. A lot of the reactions we talk about are actually going to involve water being used to create or break a molecule. When we carry out experiments, we're going to use mass to calculate the number of solute molecules in an aqueous solution. We already talked about how to find the atomic mass or atomic weight of an atom. And if you want to find the molecular mass, you're going to add all the masses of its atoms. So molecular mass is all the masses of an atom in a molecule. So if you are talking about H2O, you're going to add hydrogen plus oxygen, and that'll give you the molecular mass of that molecule. That worksheet that I provided that we started in chapter 2 has some molecular mass problems on it that you can figure out. One molecule is much tinier than what we're ever going to be working with. So typically we're not going to be dealing with the molecular mass of a molecule. We're going to be dealing with the mole. A mole is just a word that stands for a number, like a dozen stands for 12. A mole doesn't tell you weight. A mole tells you the number of molecules, just like a dozen eggs or a dozen flowers. It doesn't tell you how big it is. It just tells you I have 12 of that. When you have a mole of something, you have 6.02 times 10 to the 23rd molecules. That's a huge number of molecules, but because molecules are so tiny, that's the number it takes before you can actually start weighing them out. What you need to know is if you have the molecular mass of a molecule, that number is going to be in Daltons. If you change that number, instead of putting it in Daltons, if you put it in grams, you now have the weight of 1 mole. So whatever 6.02 times 10 to the 23rd molecules weigh is its molecular mass in grams. So that allows scientists to weigh out and measure things in the lab. Say I have 3 grams of this and 2 grams of that. I can balance my equation and have the right amounts of stuff. Molarity is the number of moles of solute per liter of solution. We're not really going to talk about molarity so much, as long as you kind of know what that word means. If you take a chemistry class, you'll get into a lot more of that. You don't have to calculate that in this class. So here, if you are calculating molecular mass, molecular formula is a representation of the atoms. So water is 2 hydrogens and 1 oxygen. So you say each hydrogen weighs 1 AMU or 1 Dalton. And so 2 hydrogens are going to be 2 Daltons. A single oxygen atom is going to be 16 AMU, atomic mass units, or 16 Daltons. 2 plus 16 is 18. So 1 molecule of water weighs 16 AMU. 1 molecule of water weighs 18 AMU. That means 18 atomic mass units, or 18 Daltons. 1 mole of water weighs 18 grams. Okay? So make sure you can calculate molecular weights and molar, the weight of 1 mole or 2 moles of something using that worksheet. So molecular weights are just calculated by adding all the atomic weights from the periodic table of whatever atom is in that molecule. Okay, I cover that. That's kind of a little bit more of a hands-on thing you're going to have to do to understand how to calculate molecular mass and the mass of 1 mole. So, if you're feeling confused, just sit down and try to work it through. Work through how we figured out this water. Work through that worksheet, see if you can start putting it together. And that's where you kind of need to make sure that you're getting it. If you were not in class, you didn't get to do the worksheet with us, and you're still not understanding it, please come by my office hours and let's work through some stuff together. Okay? Then let's talk about acids and bases. A hydrogen atom and a hydrogen bond between two water molecules can shift from one to another. So that hydrogen bond, even though it's on one molecule, it can kind of shift to another one. As a hydrogen atom leaves its electron behind, it'll be transferred as a proton or a hydrogen ion, which is written H+. The water that just lost the hydrogen ion is now not going to be H2O, it's going to be HO or OH. So that's going to be a hydroxide ion. It lost its proton. Since it lost its positive, it kept that electron. It has a negative charge, so it's OH-. Typically, that hydrogen ion isn't just going to float around on its own. It's going to go jump onto another water molecule, and that will give you a hydronium ion, a water with an extra protein, H3O+. Water is in a state of dynamic equilibrium, so the water molecules will dissociate at the same rate that they're being reformed. So on the left, you have two water molecules. On the right, you have a hydronium ion and a hydroxide ion. You can see that hydrogen just shifted from the hydroxide to the hydronium. And that's that is a reaction that is going in the forward and backward steps. So you're constantly having water break down to hydronium and hydroxide, and then hydronium and hydroxide going back to two waters. So it's at equilibrium. It is going both reverse and forward. Dissociation of water molecules has a great effect on organisms, and changing the concentrations of H+ and OH- can drastically affect the chemistry of a cell. So if you add extra hydrogens, or if you take out extra hydrogens, and you have different concentrations of hydrogen and hydroxide, you have just formed something very acidic or very basic that can not only alter the chemistry going on within a cell, it can alter it so severely that it could actually destroy the entire cell that is there. So in pure water, concentrations of H+ and OH are equal. If you add an acid or a base, you will alter the concentrations of both H+ and OH- of hydroxide and hydronium. And the pH scale will tell you whether a solution is acidic or basic. So acidic means it has an excess of hydrogen ions in it. As you see in this right side, there's more H+ than there is O-. A basic solution is the opposite of acidic. You have fewer hydrogen ions than you have hydronium ions. So you can see there's only 2 H+ and 7 OH-. In the middle is a neutral solution. There are 5 hydrogen ions and 5 hydronium ions. An acid is going to be any substance that increases the hydrogen concentration of a solution. So it is a proton donor. It just releases hydrogen ions into it. A base is any substance that reduces the hydrogen concentration of a solution. So it's a hydrogen acceptor. It pulls them out of solution, takes them, leaving you with fewer in solution. Strong acids and bases will dissociate completely in water, giving you two very different molecules that are either increasing or decreasing the pH. Weak acids and weak bases will reversibly release and accept hydrogen ions. They can still shift the balance of hydrogen and hydroxide ions away from being neutral into the territory of acidic or basic. pH is a scale that measures the percentage of hydrogen. If you've taken chemistry classes, you're going to be a lot more technical than what we're going to do in this class. What is important to know is that the concentration of hydrogen is backwards. It has an inverse relationship to pH. So as hydrogen ions go up, pH goes down. That's an inverse relationship. One goes up, one goes down. Also the reverse. As hydrogen concentration decreases, pH increases. And each change of pH is a tenfold change in hydrogen concentration. So at a pH of 6, I have 10 times more hydrogen ions than I had at a pH of 7. And if I go from 6 to 5, I've given yet another 10 times increase in hydrogen ions. So from 7 to 5, I have 10 times and another 10 times. From pH 7 to pH 5, I have 100 times change. Okay, make sure that stops and makes sense to you. One change of pH is a 10-fold change in hydrogen ions. A change of 2 pH is a 100-fold change in hydrogen ions. A change of 3 pH is a 1,000-fold change of hydrogen ions. So if I give you 2 pHs, be able to tell me which is an acid, which is a base, which is neutral, which has more hydrogen ions, which has fewer hydrogen ions, and how much has the hydrogen changed? 10 times, 20 times, 100 times? What is the number of that change? Acidic solutions have pH values less than 7. They can go all the way to 0. And basic solutions have pH values greater than 7, typically to 14. Most biological fluids are going to be pretty neutral. They're going to stay between 6 to 8. If you look at this scale on the right, you can see urine has a pH of about 6, saliva getting closer to 7. Pure water has a pH of 7. Human blood and tears has a pH of about 7.4. Inside the small intestine is getting rather basic, a little more than 8. And stomach acid or gastric juice is very acidic. That's what allows it to digest food. So that's very acidic. It has a pH of about 2. You can see some very acidic molecules would be, some very acidic substances would be battery acid, a pH of about 1. Lemon juice, a pH of about 2. Vinegar, wine, and cola have a pH of about 3. On the opposite end, very basic things that have very low hydrogen concentrations. We have ammonia between 11 and 12, bleach around 13, and oven cleaner almost 14. The internal pH of most living things, most cells need a pH to remain close to 7. Because of that, we have buffers in our bodies. Buffers will minimize changes in concentrations of hydrogen ions and hydroxide ions so that your body doesn't get very neutral or very acidic or very basic. Sometimes you'll see someone like touting a food so that you can acidify yourself or so that you can stop acidifying yourself, or this food is alkaline or something like that. That is a lot of hype because your body has buffers that keep your pH of your blood and your cells at very regulated pHs. And if you change that pH very much, you would die. If you had a pH of 8, you would not survive for very long. So your body creates buffers to keep your pH constant. Most buffer solutions are going to be a weak acid and its corresponding base, and they'll reversibly react to either accept or donate hydrogen ions. Blood has buffers to minimize pH changes. Within our bodies, the most important buffering system is the bicarbonate system. We're not really going to get into depth about it, but just be able to understand what that is a buffer and why a buffer is important. Okay, acidification is a threat to water quality. Human activities such as burning fossil fuels can threaten water quality. Carbon dioxide is the main product of fossil fuel combustion, whether from airplanes or cars. About a quarter of human-generated carbon dioxide is absorbed by the oceans. So our oceans are getting extra carbon dioxide. That carbon dioxide reacts with water to create H2CO3, which can dissociate to release hydrogens and HCO3 minus. Hydrogen can react. So you just see lots of hydrogens are going to end up as, you don't have to memorize these equations, but you get extra hydrogens being released into the water. That means that the water has gotten more acidic. Carbon dioxide dissolved in seawater forms carbonic acid, releasing hydrogen, and this is ocean acidification. As seawater acidifies, hydrogen ions will combine with carbonate ions to produce bicarbonate. Carbonate is required for calcification by many marine organisms so that they can build corals. And without that carbonate, those corals won't be able to be built. Corals also then being able to house many important organisms, and you just end up destroying the whole ecosystem there. Although science is making a lot of progress in learning about the delicate chemical balances in oceans, lakes, and rivers. The first part of this chapter, we talked about global warming and some ways that can affect life, and that hopefully your generation is able to take the science that we currently have and take it further to improve life. Hopefully this is another area where scientists of your generation are able to really find ways to take action to mitigate this problem, because right now we're losing a lot of the coral reefs that we have on our planet. Okay, so that is the end of chapter 3. I will see you next week. We'll start with chapter 4. If you have questions, please let me know, especially with being able to do those calculations for the pH scale. Sometimes that throws a lot of you off. I'm here to help in any way I can, and I'll see you in class. Bye.